Okay, let's just get right into it. What we're talking about today, it isn't just another boring incremental hardware update. No way. This is a story about a violent emergency response to a crisis that almost slammed the brakes on the entire AI revolution. This is about how engineers faced with a total system collapse had to literally rip up the rulebook and rewire the future of computing.
So picture this. Not that long ago, PCIe 5.0 was crowned the king. It was supposed to be the standard for the next decade. It was future-proof more than we'd ever need. But then, AI happened. And not just happened, it exploded with this shockingly violent force. And just like that, a technology built to last 10 years was basically obsolete overnight. So what on earth went wrong?
All right, here's our game plan for today. First, we're going to dive into the crisis itself, what I'm calling the Great AI Bottleneck. Then we'll look at the absolutely ingenious ways engineers rewrote the rules to get around it. We'll talk about a revolution in how computers use memory, the staggering new cost of all this power, and, of course, why Wall Street is completely obsessed with this. And finally, we'll see how this all adds up to a radical new blueprint for computing itself.
Okay, let's start at the heart of the problem. You've got this supposedly future-proof standard, and suddenly, engineers are watching it get completely overwhelmed, putting everything at risk. The pressure was immense.
So here's the core issue, right? You have these massive, trillion-parameter AI models running on absolute monster GPUs like NVIDIA's Blackwell. These things are so data-hungry, they could devour the entire bandwidth of PCIe 5.0 in fractions of a second. We're not talking about a slowdown here, we're talking about 100% capacity gridlock, a total and complete system chokehold.
And this quote just says it all. This wasn't some theoretical problem on a whiteboard. This was happening in the real world, where multi-million-dollar AI clusters were, and I quote, being choked to death. They were starving for data they couldn't get. The entire industry was staring down the barrel of a fatal physical bottleneck. So, how do you solve an impossible problem? Well, you get clever. You get heroic. The engineers had to throw out the old playbook and literally rewrite the rules of data transmission. And this was the fundamental challenge. For decades, making things faster was simple. Just turn up the frequency, push the signal faster. But on plain old copper wires, you hit a hard wall, a wall called insertion loss. You push the frequency too high, and the signal just dissolves into noise. It fizzles out. The laws of physics were saying, nope, you can't go any faster this way. Now, this is where things get really, really clever. The engineers made this brilliant pivot. They abandoned the old standard, NRZ, which used 2 voltage levels to represent 1 bit of data, think on or off. Instead, they switched to this wildly advanced thing called PAM4. And what it does is use 4 distinct voltage levels to encode 2 bits of data in the exact same sliver of time. And that is the genius of it. They didn't make the signal wave travel any faster. Instead, they figured out how to cram twice as much information onto the crest of each wave. They hit an astonishing 64 gigatransfers per second. It was a complete victory of logic over the brute force limits of physics. But, there's always a catch. When you squeeze 4 voltage levels that close together, the signal gets really noisy and super prone to errors. It's like trying to hear 4 people whispering at once. So to keep the whole system from collapsing into chaos, they mandated something called forward error correction, or FEC. You can think of it as this incredibly smart mathematical shield that's constantly predicting and instantly rebuilding any corrupted data without having to waste precious time asking for a resend. It's absolutely crucial.
Okay, so speed was one half of the puzzle, but the other half was just as big. The next breakthrough came from completely rethinking how computers use memory to kill this massively wasteful problem that was plaguing data centers everywhere. So just look at this slide. This shows the old, frankly dumb way of doing things. You've got server A over here gasping for air, completely out of RAM. And right next to it, server B has tons of expensive, high-speed RAM just sitting there doing nothing, and server A can't touch it. This led to companies wasting billions of dollars buying extra memory that just sat idle, like a ridiculously expensive insurance policy. And then CXL 3.2 came along, and this protocol is an absolute game changer. It takes a sledgehammer to the physical walls between servers.
It lets you take all that isolated, stranded RAM and logically dissolve it into one gigantic shared memory pool that any server, any processor in the entire data center can dip into whenever it needs to, instantly. And this is the magic trick right here. CXL is so unbelievably fast that it can grab a chunk of memory from a server all the way across the data hall, with a delay measured in nanoseconds. It's so fast that the main AI GPU is essentially tricked into believing that that faraway memory is physically soldered right onto its own circuit board. It's a merciless, brutal revolution against wasted hardware. So, we've got lightning speed and we have this incredible new memory system. But as you can probably guess, all of this progress comes at a price. A very, very steep price. Let's talk about the new cost of doing business. Yeah, the harsh reality is this whole transition is wildly expensive. Those cheap copper cables we've used for years, gone. They have to be ripped out and replaced with pricey active optical cables. You need new aerospace-grade motherboards just to handle the signal integrity, and all this generates so much heat that fans are useless. We're talking mandatory direct-to-chip liquid cooling. All told, you're looking at a 20–30% price hike for every single server. And there's another new cost, these critical little middleman chips called retimers. You see, that super fast, super dense PAM4 signal gets tired and degrades pretty quickly over distance. These chips act like relay stations. They grab that bruised, weakened signal, clean it up perfectly, and regenerate a pristine copy to send it on its way. Without these, the whole idea of a distributed server design just wouldn't be physically possible. Okay, so you've heard all the costs. You're probably thinking, why on earth is this happening then? Well, let's connect all this tech back to the money and why Wall Street is paying such incredibly close attention.
Here's your answer. The return on investment isn't just good, it is absolutely staggering. By getting rid of all those data bottlenecks, this new architecture can take an AI model that used to take weeks to train and get it done in a matter of days. Think about that. That's millions of dollars saved in electricity and getting your groundbreaking product to market months ahead of your competitors. And this has fundamentally rewired the investment world. Analysts aren't just looking at clever software anymore. They're now obsessed with something they call compute infrastructure tonnage. It's a raw measure of power. And right now, companies still clinging to that old Gen 5 tech, they're being seen as non-competitive. They're being punished in the market because in the race to AGI, they're already falling behind. So let's wrap this all up by looking at the biggest picture of all, because this isn't just about making faster parts for the same old computers. This is about a fundamental redefinition of what a computer even is anymore. This slide really says it all. The old model of a server was a box, a self-contained box of isolated parts. The new model, thanks to PCIe 6.0 and CXL, is something else entirely. It's a single, distributed, interconnected digital brain. A nervous system that spans the entire data center. It has mutated from a box into a brain. But, of course, if you have a distributed brain with thoughts flying between different parts of the room, you create a brand new lethal security risk, physical wiretapping. To absolutely annihilate this threat, the new standard mandates something called ID. It's hardware-level AES 256-bit cryptography that encrypts every single bit of data as it flies between servers. So even if someone manages to physically clamp onto a cable, all they'll get is completely useless encrypted gibberish. And that brings us to our final thought. Let's be perfectly clear. This technology isn't a luxury. It's not a nice-to-have. It is the absolute singular salvation strategy to keep the progress of AI moving forward. Without this, everything grinds to a halt. So as we build this global interconnected brain, we have to ask ourselves, what does it mean for all of us when access to this incredibly complex and expensive hardware becomes the mandatory, non-negotiable price of admission to build and even participate in the future?